Good. Let's continue with our second speaker, very well-known local from Nordita, Paolo Di Vecchia, telling us about classical observables of GR from scattering amplitudes. The stage is yours.
Doesn't seem to work. Click. What do you mean?
Let's see if it will.
Not left, not right.
Yeah. Oh.
Up and down to the base.
Yeah, that's.
But this doesn't work.
No, that doesn't work. Okay, so I think the organizer that put up this meeting were different direction in quantum gravity are discussed. And I thank also for giving me the possibility to come here and give a talk. Unfortunately, there is a very little quantum in my talk. Eventually, you will see some quantum, but not so much. So what I'm going to talk is practically classical. So how do we extract classical observable in general relativity using scattering amplitude? Now, what I'm going to talk is mostly in the paper that many papers that I wrote with Carlo Heisenberg, Rodolfo Russo, and Gabriele Veneziano, and there is now a review in Physics Report that appeared a few months ago. And I will talk also on two more recent work with Francesco Alessio and with Carlo Heisenberg. So that's the first events that has been observed at LIGO. And for the first time has been observed that we have gravitational wave, and gravitational wave have been detected. And that means that we have to develop the theory in such a way that we can compute more precisely various observable in such a way that we can compare with what we get from the experiment. And essentially, we have to do this calculation and extract from the theory the waveform of the gravitational wave to be compared with what you observe in the experiment. In the past, this has been mostly done in solving the Einstein equation in the presence of matter. And let's see if... yeah, it seems to work. Okay, so you write the Einstein equation with an energy momentum tensor and expanding the metric around the flat space and choosing the harmonic gauge. You get this equation. Then maybe it works. No, that doesn't work. And then you get the solution is given by in terms of the retarded Green's function. Then you expand for large distance, and you get an expansion in multiple. And the lowest one is the quadruple, that in the transverse traceless gauge is given by this expression in terms of the angular moment, of the energy momentum tensor. So this calculation uses the post-Newtonian expansion. This is an expansion for small velocity and for small field, most potential. And there is a very good, very interesting review by Blanchet that if you are interested, you should look at. Now, if the gravitational waves arrives, then if you have a free-falling particle, depending which kind of polarization you get a modification of the circle. For the cross, for the plus and the cross polarization. And that means that you have an interferometer here where you have a laser, you send light. Here the light is split 50% in this direction, then the light comes back and is observed here. And now, if there is a gravitational wave arriving, then the metric is not anymore the flat metric, is changed. And so you have to use the metric to compute the distance. And so you see that there is a larger distance in this direction than in this direction. And you see a pattern here when the light arrives here. And that's the way you detect the gravitational waves. And actually, the amount of difference that you observe in the experiment is extra. It's very, very small. The difference in distance is of the order 100 or 1000 on the proton dimension. So it's really a spectacular experiment. Now, recently, a complementary approach has been used to extract classical quantity from the quantum scattering amplitude using the Post-Minkowskian expansion. In using amplitude, essentially, you always gauge invariant quantity. You don't have to worry anymore about gauge fixing and all the stuff. Now, when the two black holes are far away from each other, one can use perturbation theory, expanding in power the Newton constant, and you get a post-Minkowskian expansion. When they get closer to each other, the interaction becomes so strong that the only way is using numerical relativity. So you solve the Einstein equation numerically. And there is also a very good, interesting review here recently in the net. Another very useful approach is the so-called effective one-body formalism introduced by Bonanno and Damour. One constructs an effective Hamiltonian for a particle with mass of this mass in an external metric that is fixed by requiring that the effective dynamics be the same of the original dynamics. It leads to results faster than numerical relativity, and there are interesting papers that I will come back later. This effective one-body waveform are an important class of in spiral merger ring-down waveform used for the LIGO-Virgo search. And then there is a self-force approach. You start from a mass much bigger than the other and a metric generated by the large mass, and then you compute correction to this mass, to this metric produced by the small mass. So these are essentially the approach that are used. Now, in this seminar, I will be describing the two black holes with two spinless particles with mass M1 and M2. And I will consider the scattering rather than the merging. There are techniques to allow to go from the scattering to the merging, but I don't have time to discuss them. And I will consider the elastic and elastic scattering, production of an extra graviton. In the case of the elastic scattering, I'll show that the physical observable was the classical deflection angle can be computed from the eikonal. In an elastic case, the eikonal becomes an operator containing the gravitation, creation, annihilation operator. I will limit myself to the case in which the emitted graviton is soft, computing inelastic observable as the waveform and the linear and the angular momentum. Now, so I start to discuss the leading eikonal. You start from the three-level scattering amplitudes with, this is essentially a vertex with one graviton exchange. And I will concentrate on the non-analytic part. So I neglect terms which are analytic. And the amplitude depends on q squared, the momentum transfer, and sigma, which is defined here, which is essentially a function of S. And that's what you get in the high energy limit. Now, this process involves the exchange of a single quantum graviton. Then we can go to impact parameter, constructing the eikonal, and is constructed using this formula. And essentially, you have a Fourier transform in the two transverse direction in 4 dimensions, and that's what you get. And you see that this is the leading eikonal and is divergent, and this has to do with the long-range Newton potential. And this quantity is dimensionless and is proportional to 1 over h bar. In the classical limit, it is natural to take B, sigma, and the length scale, which is analogous to the Schwarzschild radius, to be the classical quantity. And then you can rewrite the eikonal in this form. And the regime that we are describing here is a regime in which B is much bigger than the Schwarzschild radius, which is much bigger than the quantum correction. So for h bar small, this is a big quantity, and this factor signals that this quantity should appear in an exponential. So we can describe the value of the classical action. And in fact, these people, Cabot and Ortiz, show that summing all this diagram and also the cross diagram, you can show that this diagram exponentiates. And so they show that there is an exponentiation. On the other hand, if you assume the exponentiation, you fix the leading high energy behavior of the multi-loop amplitude. So after the eikonal resummation, the leading contribution to the S matrix is captured by the phase, which effectively resum infinitely many exchange. How can you see this? Then you go back to momentum space here. And so it's again a function of Q, momentum transfer. And you compute for large B, the Fourier transform can be computed, is dominated by the saddle point. And so the saddle point equation is this one. And while the Q that I had in the propagator before is a quantity quantum, which is order h bar over B, this quantity is classical because the h bar here cancels the 1 over h bar that was in the eikonal. So QS represents the momentum transfer in a classical deflection, and is also called impulse. Now, if you take the ratio between this QS with respect to the typical momentum of each soft particle, you get a quantity, we get the average number of exchange, graviton exchange in the classical in the classical limit. And this expression diverge when h bar goes to 0. So it's infinite. And then from this Q, you can compute the deflection angle using this formula. And you get something which is classical, doesn't depend on h bar. And this is the deflection angle in the keeping the leading eikonal. Now, in conclusion, this is the momentum transfer in the classical expression, and it's straightforward to generalize to discussion before 1 p.m. One need this expression. You can put the complete eikonal. So, but how do you compute this eikonal? Now, these are so I have extracted the leading eikonal from the tree diagram. So the non-leading eikonal, the next to the leading and the next to the leading is extracted by the loop diagrams. So the loop diagrams contain classical quantity, and we have to extract this classical quantity from the quantum scattering amplitude. So if assume the eikonal exponentiate, the amplitude in parameter space has this form, where this is the complete eikonal, and these are the quantum correction that appear in the complete amplitude. And so we have to, starting, you do a loop calculation, you compute the amplitude, you take away the quantum part, and you extract the classical part. For instance, no. So if you expand at order G, you get this, the amplitude that gives directly the eikonal. At order G square, you get, this is the amplitude. Then you get a term which goes 1 over h bar square. And then you get a term quantum, which orders h bar to the 0. And the term 1 over h bar is the next to the leading eikonal. If you go to two loops, then there is a term which goes 1 over h bar cube. There is a term 1 over h bar square, which is a two-particle cut. There is a term of order 1 over h bar, but you have to take away this term, which is also 1 over h bar, but does not contribute to the eikonal, and so on. And in this way, you extract from the scattering amplitude the next to the leading eikonal, and then the classical the impulse or the momentum transfer is obtained taking the derivative of this eikonal with respect to b mu, and then you compute the deflection angle. Now, the previous exponentiation is certainly correct up to two loops, but there is no proof that it continues to be valid to higher loops. In fact, in this paper, in the n=8 supergravity, N and somebody else, they computed three-loop amplitude. They compute all the integral in the three-loop amplitude. And in this paper, there is a term that we cannot fit with the exponentiation. So this is an open problem that has not been solved yet. Now, the subleading eikonal is extracted from one loop diagram, and this is the result. So you get, this is order Gn, this is order Gn E m so over b square. So the eikonal and this factor are dimensionless. And then from the second term, you get the impulse at order G square. Now, let's go to two loops. Now, the subs, so I will show you that we can extract the next to the next leading eikonal at two loop from the three-particle cut plus real analysis. So the sub-leading eikonal come from the two-loop diagram as an imaginary part. This imaginary part can be computed from the three-particle cut at the unitarity relation. And here is the sum of polarization. If you do the calculation in n=8 supergravity, you have to sum over various massless states. In GR, you sum over the two polarization of the graviton. And this diagram is computed putting together two 5-point amplitude. This is a 5-point amplitude with 4 scalar particles and 1 graviton. And you have to glue these together. So you have to know what is the 5-point amplitude that I wrote here as a function of the momentum. And this amplitude is gauge invariant. And depending if you have GR or n equal 8, this factor here is different. Here you have, in GR, you have to subtract the dilaton. So you put this amplitude in the 3-particle cut, and then you get the imaginary part of the eikonal in terms of the classical 3 5-point amplitude impact parameter space. So this is the 5-point amplitude, and you go to impact parameter space. And this expression is very powerful because it allows to compute the imaginary part directly from unitarity without needing to compute a complete two-loop amplitude. Okay, so in GR, you have sum of the polarization. In n equal 8, you have graviton, dilaton, 2 scalar, and two vectors. Now, this imaginary part is infrared divergent. There is a factor 1 over epsilon. But it turns out that the infrared divergent part is completely determined from the leading soft term of the 5-point amplitude. And this is the quantity I want to compute. So in the soft graviton limit, the 5-point amplitude is this factor, which is 1 over omega, times the elastic amplitude. And then in the classical limit, you have to expand for small q, and that's the quantity you have to put in the 3-particle cut. And then you do the calculation, and that's what you get in terms of this function I of sigma. And because of the imaginary part, the eikonal is not unitary anymore. So we compute the imaginary part of delta 2, but we want to compute the real part because that gives the observable. And at this point, now the deflection angle at order G cube was computed in a spectacular paper by Bern and collaborators in January 2019. And they compute the loop integrals, a two-loop, approximating the loop integral in what is called the potential region. So this is a particular approximation of the integrand of the loop that appears at two loops. But it turned out the deflection angle was infinite at high energy. So if you take the expression computed in this paper, they get infinite quantity when the energy goes to infinity. And this was in contradiction with a paper by Amati, Ciafaloni, and Veneziano, where the deflection angle was computed in a massless case and was finite. And so there was an infinite long discussion that lasted almost a year. Some people say that you cannot compare, other people that something was lacking in this calculation. Eventually, the problem was solved because we computed in n equal 8 supergravity the same quantity, and we found that the potential, you compute the loop diagram using the method of the region, but the potential region was not the complete expression. You need to add also the soft region. And then when you add the soft region, you get extra term. And when you put this extra term in the n equal 8 supergravity, then you get something which is finite at high energy. And this was the way to obtain what now we understand was the radiation reaction that for the first time appeared at two-loop level. Now, the person who immediately understood the meaning of our calculation was Thibaut Damour, and he used the linear response equation involving the loss of angular momentum at order G square to compute directly the radiation reaction in GR, finding a finite result at high energy. Now, instead, we use argument based on real analyticity, and we argue that the expression that one should get was this. This was obtained from the imaginary part. There is an I. So we knew this. And this is obtained by this integral that is divergent. But there is an upper limit here. And this limit gives this quantity here. And then with some calculation, we argue that this quantity is this. And reanalyticity implies that if you go from the region above the cut to the region in which there is no cut, there is 1 over pi. So we got this 1, and this 1 gave us the real part of the eikonal. And in this way, we extract the real part of the eikonal, and then we got this deflection angle, and we got the same result as Thibaut d'Amour. So this is the two-loop eikonal. There is a part that comes from the calculation of Zwieber et al., which come from the potential region, and the blue terms are the ones which come from the soft region. And when you add these two terms, there is no problem anymore at high energy. So this is the status at, this is 3 level, 1 loop, and this is 2 loop. And the green and the black are computed in this paper, and the blue is the radiation reaction. So anyway, at this point, there is no doubt that everything is correct. In fact, there are many papers that extracted the classical limit from the loop amplitude, and they checked that the next to the leading eikonal was correct. And now there are also complete results at 4 p.m. of different groups. They claim that including also radiation, and at 4 p.m. there is again the problem that at high energy the deflection angle diverges. And this is something that does not be understood yet. Now, if you don't integrate over the momentum of the graviton, you get a differential spectrum of the number of emitted graviton, which is goes to infinity, 1 over h. But if you multiply by the energy of the graviton, h bar omega, the h bar goes away, and you get the spectrum of the energy. And this is a classical quantity. If you integrate over the angles, you get the spectrum of energy as a function of omega. And for omega equals 0, you get the zero frequency limit, that this is the quantity that I want to compute. So, this, I start to talk about the inelastic case. So, and I will restrict to the soft. So the omega is very small. So the S matrix element for emission of n soft graviton factorized as the product of term of this kind times the amplitude, the elastic amplitude. And I want to write an eikonal operator that reproduce this result. And then I will use it to compute an elastic observable, like zero frequency limit of the spectrum, the linear and the angular momentum up to 3 p.m. So you introduce the creation annihilation operator for the graviton, and where delta is given in this expression, and I restrict to soft graviton. more explicitly, this is a dimensionless quantity for this quantity means less than 1. And then I'll follow the approach of Bloch-Nordsieck, and the scattering, the S matrix is given by the product of the part which describe the emission of soft graviton and the part which describe the elastic scattering. And so introduce this operator where this integral is this one, and then the S matrix for the emission of soft graviton is given by this quantity here. This is the elastic amplitude, and we have to divide by this factor because when you normal order here, you get you want to get rid of this normal ordering. And then with this expression, you can saturate with a graviton annihilation operator, and you can check that you get the correct amplitude in the soft limit. Then you can go to impact parameter space, and the question is that you have to remember that this quantity W contain the momentum of the particle. They are related in this way, but rather than to use P1 and P2, I use P1 tilde, P2 tilde. Essentially, people learn by now that there are two impact parameters. There is this B that it's orthogonal to P1 and P2, but there is a BE. Is that what the B that you get in the eikonal, which is orthogonal to P tilde, which is P2 tilde is around this direction, and P1 tilde is around this direction. And then you write in terms of the P1 tilde and P2 tilde and Q, and then you trade Q in the going to the impact parameter space by writing instead of Q the derivative with respect to B, and this derivative acts on the eikonal. Now, because of this factor, you get only the real part of the eikonal, of the C number eikonal, and then inside this quantity there is Q, and you substitute Q is this d over dB, but d over dB will act only on this quantity here, and you have to be careful that 1 over h bar cancel h bar in order to get a classical quantity. And then at the end of the calculation, what it means that you get, instead of P1, P2, you get essentially P tilde, and in terms of the deflection angle, the classical deflection angle. And now the S metric is unitary because the imaginary part is obtained when you normal order the oscillators. Okay, I've already mentioned, and the imaginary part is this, and this is the same expression that I got with the three-particle cut. Another quantity that you can compute is the momentum of the field that is given. You insert this in here, and you compute, you get this quantity, and you can check that this can be obtained from the previous quantity, the imaginary part of the eikonal multiplied by epsilon, so eliminate the divergent term, and that gives the zero frequency limit of the energy emitted spectrum. And so for the 2x2 case, you define these quantities, and you get that quantity, which is function of q square and the mass of the particle. And this formula is exact. If you assume that q square is much smaller than m1 and m2 square, then you get this expression here. Now, up to now, I've considered soft graviton, but non-static. Now, there is, so the previous soft eikonal is based on the standard Weinberg theorem, which includes soft graviton, but not with low, but not non-zero frequency. So it doesn't include effects that arise due to the exactly static field, which is localized at zero energy, zero frequency. To include this is sufficient to replace the standard soft factor by the I over I epsilon prescription. And you consider, instead of, this is the previous operator, you insert this factor that you see does not appear if you neglect this I epsilon. But in order to take care of this, the possibility of having graviton exactly at zero frequency, then you insert this, and and then you get quantity which are localized at omega equals 0. And you compare with so you compute this quantity here, and you discover that this quantity here that before was having all the radiation now includes all the conservative part of the radiation. Okay, this is a... But then you can compute observable, and one of them is the angular momentum. You can insert the angular momentum here. You get this in the two-particle scattering, and when you insert the momentum transfer at 1 p.m., you get this loss of angular momentum, and that exactly the quantity that Damour used to compute the radiation reaction. If you insert the impulse at one loop, then you get J order G cube, which correspond to the static term computed in this paper. So these static quantities come naturally from amplitude approach and are physical quantity. In the frame of GR, people are still debating about their physical meaning. They are debating how do you define the angular momentum. You start with this paper. Now people start to find way to show that even in GR approach, you can give a meaning to this quantity. And this is the last paper that appeared that for me is very difficult to read, but it's nice to see that the GR community is converging to results that have been obtained from the scattering amp. Now you can compute the linear memory, so the waveform. So you can construct the metric fluctuation called the waveform at large distance from the stars by multiplying. So people have computed this using solving the Einstein equation. Instead, you essentially, instead of putting the energy momentum tensor, you multiply this quantity with the scattering amplitude, and that's what you obtain in frequency domain. And it's a function of the distance and the angle in which you observe the radiation. If you keep only the leading soft term, that's what you get. And this is a projection over the two transverse trace component. And but you can go to time domain, and you get the leading soft behavior, and this is what is called the memory effect. So that consists in a permanent change of the metric to the passage of the gravitational wave. Now, let me go, and this is the point in which they have loop diagrams. So at the tree level, gauge invariance requires that the amplitude for the emission of soft graviton can always be written in this form. There is a term 1 over omega. There is a term omega to the 0 and a term omega to the 1. And this can be derived by gauge invariance, so assuming that K mu and mu nu is 0. Now, these are the three levels. If you go to one loop, then you have infrared divergence that were computed by Weinberg in 1965, and that modified the soft theorem. And Weinberg showed that an endpoint amplitude has an infrared finite piece multiplied by an exponential, and the exponential, this W, is given by this one loop diagram. And this is the only source of infrared divergence that appears at any loop level. So this integral can be computed, and that's what you get, and that you can rewrite in this simpler form, introducing the sigma. And you have here an ultraviolet and infrared regulator, and these are connected to the dimensional regularization by this formula. So you can also do the limit of zero mass of this expression. So it's one of the particle, external particle at zero mass, and you get a finite result. There is a term log m, but cancel, and that gives the scale here. And this is, if you do the same kind of things in QED, you get, it's not, doesn't go like in gravity because of collinear divergences. Now, all these kind of things can be found in Weinberg paper. There are more recent papers of this approach. These are the paper. And also, these are connected to the many papers that Lada, Sen, and Tsao wrote. So there is a convergence of result, but more or less everything was essentially in Weinberg paper. Now, in the classical limit, the log part of this term can be neglected. And in the classical limit, these are the two expressions for the one loop diagram if you have a massive particle, and this if you have a massless particle. And the infrared cutoff has been chosen to be omega, the frequency of the emitted graviton. And the fact that in the classical limit only these two terms appear is a consequence of writing the form momentum of the graviton exchange in this form, where you send h bar to 0, keeping omega finite. And then you get the Mn is given by this factor times something finite. And then n plus 1, where you have one massless particle, you have to do this factor for the massless particle. And then this term you can be written in this form, where you include the soft term that appear in the previous transparency. At the end, you have the amplitude with n plus 1 graviton in terms of the amplitude without a graviton, in terms of the soft factor, and these terms which come from the loop correction. So this is the way that the soft theorem is changed, going from the tree level to the loop level. And so if you expand, you find various terms. And however, before there was a soft theorem in 1 over omega, omega to the 0, and omega to the 1. When you go to impact parameter space in loop space, the regularization procedure, you see that the term proportional to omega to 0 is not anymore universal. And actually, in 4 dimension, also the eikonal, you have to regularize if you go to 4 dimension. And so the universal term are not anymore 1 over omega, omega to the 0 and omega to the 1, but becomes 1 over omega log omega and omega log omega square. And this is all one gets according to this paper. However, there is not anymore a general theorem that you can deduce from gauge invariant to show that this term is universal. Now, this procedure gives also term like that, but one gets additional term. So that means this term are not universal, in the sense that if you compute the explicit amplitude, you get not only the universal term, but the additional term. And so what I'm going to do now, I am going to use this extension of the soft theorem to compute this quantity at higher loop. So up to now, all this quantity have been computed at the tree level at one loop, and using the eikonal exponentiation. So the important point that I put for the amplitude Mn, the eikonal resum amplitude. If I put this, then I can have a prediction from the soft theorem. What are the waveform? What are the if you compute the waveform, I can get the term log omega, omega log omega square, and 1 over omega directly from the soft theorem. So you can compute this term either by explicit calculation, computing the waveform, the 5-loop amplitude at 2 loops, or you can use the soft theorem, but you get only the soft term. In the other case, you get the whole waveform. So I just give some result, and so I write the momentum in this way. At the tree level, this log omega gives this quantity here, where G1 I multiply by the polarization of the graviton. At one loop, I get this, and these are more general expressions which are gauge invariant. And at 2 loop, I get this in terms of this gauge invariant quantity, where Q2 is the momentum transfer at 2 p.m. You can do also for the term omega log omega square out one loop, and that agrees with the explicit calculation, and this is the new result that one gets from the 5-point amplitude at 2 loops. And for the 1 over omega term, there is this term at 3 level and 1 loop, putting the impulse at 1 p.m. or 2 p.m. And this is the two-loop expression where you have for the nonlinear memory at 2 loop. So the nonlinear memory is something where you have to consider emission of graviton from other graviton that is not included in this calculation. All the previous result at 1 loop agrees with the explicit result obtained in this paper. And we obtain also the universal part that agrees with this paper. And we have checked this expression going to the 0 pn. So you take the classical limit, you take the Newtonian limit of the expression, and in the Newtonian limit, these two-loop amplitude agree with the Newtonian calculation at the leading order. Okay, maybe, okay, we compute the soft spectrum, but so what I want to, at the end, discuss universality at high energy. In gravity, the massless particle with highest spin is the graviton, and the theory with massless particle with spin 2 is consistent only if it's invariant under any choice of coordinate. There is no way out of this. Since we expect at high energy the massless particle with highest spin dominates, we should get in this limit a universal behavior of the various observable. And we have seen that this happens at 3 p.m. for the elastic process. Doesn't seem to happen at 4 p.m. The question is it valid also for inelastic process with emission of extra graviton? Now, I limit the analysis to the soft case. If we see that in case of inelastic process, universality is also recovered, but this way in a very non-trivial way. So what happens is that the PM approximation breaks down even when the deflection angle is small, but the energy is high enough. And this happens when this quantity is bigger or equal to 1. You see here, even if the deflection angle is small, you can go to very high energy, and this becomes bigger than 1. This question is discussed in a paper by Ditt and Kovac-Thorn. And let's see what happens if you look an observable like the zero frequency limit of the spectrum. So this is the complete expression. And the last line, because of this term here, diverge when q squared becomes minus 4mi squared. It's a non-physical value, but still there is a divergence there. Now, if you do the high energy limit, assuming that q squared is less than the mass, then that's what you get. And that's what you get in massive supergravity. But since this cosh, it's essentially log s over m1 m2 squared, you see that it's singular when you take the mass equals 0. So you cannot go to the massless case, and this is due to the approximation that we made here. But if you instead you keep the expression complete, and you take the high energy limit, and also the possibility that the mass is smaller than q, then you get instead this quantity here, which you can show is equal to this, that agrees with the contribution of the leading soft term computed by Sao Sen with completely different methods. And at the leading order in theta s, you get this, which agrees with result obtaining from classical GR in this paper by Gruzzinov and Veneziano. So the same result is also obtained in this paper. One obtains a quantity in terms of classical quantity, which is perfectly well defined in the ultra-relativistic limit. And the same happens for the angular momentum and also for the waveform. And if you do the same calculation in n equal 8 and do the same procedure, you get complete universality at high energy. In conclusion, going over the bound of Ditt and Kovacs and Thorne, one recovers universal behavior, but the PM expansion breaks down even when theta s is small. So I came to the conclusion. So we have constructed the eikonal C number and the eikonal operator that reproduce all data up to 3 PM. We have used the eikonal exponentiation, the soft theorem, to compute the universal part of the waveform up to 2 loops. Since in theory the graviton is massless part, we expect universality, and this can be achieved if you have to go over this limit. In this regime, we cannot neglect q squared with respect to mi squared. So the PM expansion is not valid anymore, and we get a non-perturbative answer, essentially because you get log of the Newton constant. This may be also the solution for the energy crisis problem. From this calculation, if you compute the total radiated energy divided by the energy that you put in, you get something which diverges with the energy. So you get more energy out than you put in. So this is trivially wrong. And the same up at 4 PM. And also at 4 PM, the deflection angle diverges at high energy. Now, all these things may be cured by the method I mentioned before, or may need better understanding. Actually, we need more data at the level of numerical relativity to be able to get at higher energy. And in fact, I want to conclude with this picture that are in this paper. So in this paper, essentially, they compute the deflection angle as a function of b, more or less. This is large b, and this is small b. And you see that you put 1 PM, 2 PM, 3 PM, and also 4 PM. And these are the point of numerical relativity. And when you put 4 PM, you get much better agreement than if you don't put in this diagram. But there is another diagram where you compute as a function of the velocity, this is the angular momentum below which you get capture, and above which instead you have scattering. And you see that this quantity from numerical relativity is almost constant, but from 4 PM result goes higher up. So there could be a sign that something has not been yet understood at 4 PM level. But most of the people are not worried about this, and they are computing for loop now. And eventually we'll have a for loop level. Okay, that's all I want to say. Thank you very much.
Thank you, Paolo. We have time for maybe one short question again. Yeah, Luca.
So most of the discussion, of course, is at some point you mentioned n equal to 8 supergravity to check basically this radiation contribution. So do you mean that basically you took n equal to 8 supergravity just to do the computation and then take a GR limit? That was the idea?
No, you take annihilate supergravity, and you do the classical limit like you do in GR.
Okay. So you just as a tool.
Yes. It's another theory that you want to compare to see if at high energy you get the same behavior. I mean, whatever theory of gravity, the principle that I'm using, whatever theory of gravity you compute something, if you go to high energy, you get universality. And that is something that one can check.
But what was the need of using like n equal to supergravity to basically solve this puzzle of the radiation?
I mean, the n equal h super. The reason was that there was a previous paper done in n equal h supergravity where the computation, the potential was already done, and so the only thing we need to do is to compute in that theory the soft to compute the loop integral using this technique of the differential equation using another region, which is a soft region. So when you do, when you compute loop diagram, you approximate the calculation. You say, okay, I want to compute something in a classical limit, so you approximate the loop integral in some way. And that was the approximation done in the previous paper, or n equal h supergravity. What we did, we noticed that there was a region that was neglected that gave also classical contribution. We computed the expression in this region, we added to the result on the previous region, and then we showed that the deflection angle was not divergent. And that was done in this theory because it was easy to do the calculation.
Same result, same computation also performed by Damour in the standard GR.
Yes, Damour understood immediately that that was the radiation reaction that was neglected. And he knew an alternative way of computing. Yes. Yes. Yes.
Brief or
yeah, I think it's
okay.
So what goes into these amplitudes are essentially tree level and there are loop corrections. But how does this match with if you actually compute in GR, you would have divergences, and you have to use higher loops to extract classical paths. Can you sort of disentangle that and see that there are no consequences of any divergences?
Which divergence? Ultraviolet? Yeah. Well, up to now, we have not seen any ultraviolet divergence. On the other hand, I expect that eventually, even if you go to large B, you see the eikonal, the leading eikonal is valid at large B. The next to the leading is you get closer and closer to B equals 0. So eventually, since we are having a theory with a point-like particle, we expect that at a certain point, we have also ultraviolet divergence to compute classical. But this is not in contradiction with anything. I mean, if you took Landau Lifshitz book, you see that there is a classical electron radius from QED, and you have the classical gravitational radius from GR. Up to now, we have not noticed.
Okay, let's thank Paolo again. And we continue at 11:45.